Hi Malcolm.
Hola.
What are you doing here?
Damn good question.
Aquest vídeo és una entrevista amb Malcolm Hillebrand. Ell és un matemàtic que va fer el seu doctorat a Cape Town, a Ciutat del Cap, a Sud-àfrica, d'on és ell originàriament, i ara és aquí, a Dresden, Alemanya, fent un postdoc al Max Planck Institute for the Physics of Complex Systems. Ell treballa en sistemes caòtics, treballa amb la teoria del caos i l'he convidat per parlar exactament d'això. Hem parlat de què és el caos, quins ingredients ha de tenir un sistema per ser caòtic, hem parlat de caos i fractals, hem parlat del famosíssim problema dels tres cossos i del nostre sistema solar, a veure com acabarem. I, evidentment, també li he preguntat per la seva recerca, en quins sistemes treballa, i he après que el caos està per tot arreu, fins i tot als sistemes vius. És una entrevista carregadeta, així que agafa un té, apoltrona't al sofà i disfruta de l'entrevista. Està buida. Let's talk about chaos. What is it? What's chaos?
Chaos is really unpredictability. So it's this idea where a small change in the input produces a big change in the output, right? So the classic example is this butterfly effect, where a butterfly flaps its wings in Kyoto and causes a hurricane in Texas, right? So where this really, really small change produces a big effect.
This is super counterintuitive, I find, because like a very small breeze that that is almost not perceptible, like the flap of the wings of a butterfly. How can this create a hurricane? How does that happen? Why is chaos so unpredictable, and why? It's so amazing.
Yeah, it's super weird, right? And I think, even for me, I've studied this for several years now, and it makes even less sense now that I understand more of it. But it really is this sort of amplification of a small perturbation, right? Where it's this idea we tend to think our brains are very linear, and I think, if I make a small change, it'll grow in a small way.
That's logic, right?
Yeah, exactly.
So chaos breaks this logic.
Yeah, precisely. And so it's super weird and hard to be intuitive about, but it's super exciting because of that.
Okay, so it amplifies any tiny change. It amplifies exponentially?
Yeah, exactly, exponentially.
Okay, that's the problem.
Exponentials
are the problem.
Yeah, exactly.
In my earlier video, I talked about butterfly effect, but one comment that I got from someone, and I think they are right, is that there's this misconception that when you talk about the butterfly effect, it looks like the butterfly causes the hurricane, and there's this relation cause effect between the butterfly and the hurricane. Is that a misconception? Because then it's
we should go kill all the butterflies, right? Stop hurricanes. Yeah. I think the key thing here is that with chaos, you have very complex systems. So you have many things interacting, causing things, right? So the reason that butterfly's wing flap causes the hurricane is because of all the other things happening in the system that is our wonderful atmosphere. Right, so you could just as well blame the clouds as blame the butterfly.
Okay. Let's not blame the butterflies.
Yeah. Let's not blame the clouds either. But it's just the system is chaotic, and so then any small change by any agent can do that.
What makes a system chaotic?
I think perhaps this one simple way of thinking about this is that if you have many things interacting, you're extremely likely to have the potential for chaos.
I see.
And so in the atmosphere you have that, for example. And if you have a small control system, then with forces or interactions which are not really non-linear, which behave in a way that you expect, then you would generally not get chaos. But when you have lots of interactions, it's one of those things where actually, I'm surprised we don't see more chaos. Because when you start thinking about it, you have electrons bouncing everywhere, you have, everything has some electric charge, everything has some forces, right? Yeah. And it's bizarre to me that actually, why do things behave? Why does my hand hold together?
Wow, that's so surprising. These are like the ingredients to have a chaotic system, like many components, nonlinear interactions, and maybe more, no?
Yeah, I think that's probably a pretty good sort of minimal recipe for chaos, right? That if you have, so you don't have to have a lot of components. If you have sort of sufficiently non-linear forces, then even just a handful of things, right? You can think of a star orbiting, a planet orbiting a star. You can tell I'm not an astronomer. A planet orbiting a star, and if you just have two bodies, then that's nice.
Yeah.
Add the third body, and then suddenly, bam, everything goes out the window, right? And so then, and this is actually something that's very interesting about chaos, and where it's useful is to understand these kinds of orbits, right? Where you can say, okay, is this planet's orbit stable? And so, for example, it's quite important to us to know, is the Earth stably orbiting the Sun, and this kind of thing. And you have just a handful of planets interacting, and this can cause chaos.
My gosh.
But it doesn't have to. So you can have, so for example, the Earth is not about to slingshot off and leave the solar system, but you really don't need that many ingredients to make chaos. But the more interactions you add, the more likely you are to have chaos.
Okay. That's super interesting. So let me just recap what you said, because it's quite shocking to me. So you have a star and you have a planet orbiting. This is perfectly stable and it's not chaotic at all, or everything is predictable. But then you add a third body, and then the whole system becomes chaotic.
Yeah.
And if you add a fourth, becomes, so it's even like worse. So these are, we have like three elements. We don't have more particles. We have like a sun, a star, a sun, a planet, and another planet maybe, or a moon.
Yeah.
And that becomes chaotic.
Yeah.
That's so surprising.
Yeah, and the thing is, like, there's obviously chaos and there's chaos. So there's what we could call weak chaos, where if you just have a sun, a planet, and a moon, maybe the moon is quite light, so it doesn't have a very strong effect. And then you kind of have this weak chaos, this weak non-linearity, where you do have it, but not so effective. But then you do get cases where maybe you have a whole bunch of different things interacting, and then it's really, really clear that to predict the path of an individual planet is really hard, and if you tweak it slightly, you could get something completely different. Okay.
Is our solar system chaotic?
Yeah, in principle.
Okay. When are we going to crash?
Actually, people have computed this, and it's like billions of years or something.
Okay.
So you can compute the Lyapunov time, which is what it's called, of an orbit, which is how long it takes to become chaotic, and we're good.
We're good. Okay.
Yeah.
That's a relief. That's nice. So I talked about the Lyapunov time in my earlier video.
Nice.
But it would be great if you can explain me what Lyapunov time means.
So I think let's actually stick with this planetary orbit example, because I think it's nice clear. It's really the horizon time for when a process becomes chaotic, or the chaos becomes evident. So let's say I'm happily orbiting my star, delete, everything looking good. And then after some time, I'll start perturbing from that orbit. I'll start going away from that nice stable orbit, and then suddenly it spirals out of control and I go away. And so that time before chaos sets in is what we call the Lyapunov time.
I see.
That's basically the explanation.
I guess the Lyapunov time is shorter or longer depending on the system.
Exactly.
And from some systems it's like super evident, super fast that it's chaotic.
Yeah.
Like maybe like a double pendulum.
Yeah.
It's one of the classical examples of chaos. And Lyapunov time, it's quite pretty easy to see, no? I mean, I've seen many examples of people like at home, like doing this experiment. You just play it and it's crazy.
It's super cool.
Woo! Starts doing some crazy stuff. Very soon. There's another aspect about chaos that I really love, but I've never understood, which is the relation between chaos and fractals. I know there is a relation between these two phenomena in math. I mean, in the math that is governed the other way around, the math that governs chaos, or I don't know how you see that. This is too philosophical.
I
don't know. But But you know, the math within chaos and math in fractals, like how are they connected? I hope you can help me understand that, because I'm very curious.
This is super fascinating. I think like fractals are really beautiful. I think most people, you have some idea of a fractal, maybe this Mandelbrot set, or even like the classic example of the coastline paradox, right? Where if you look at the coastline of an island and if you measure it as like a rough scale, you get one thing. If you zoom in and you now start counting every little corner, it gets longer and longer. And so this is this sort of weirdness of fractals. But then chaos, if you remember what I said about chaos at the beginning, was that you have this sensitive dependence on initial conditions. So small change in input, big change in output. And so then I think one example of a fractal causing chaos is that if we think of a surface and I drop a ball on the surface. If it's flat, then I know exactly what happens every time I drop the ball. A small change in where I drop it doesn't make a difference. If I just have a single triangle and I drop it, I know as long as I'm on this side of the point, it's going this way, go this side, goes that way. And otherwise, a small change doesn't make a big difference. But now imagine, take this picture of a fractal that we have of this very jagged sort of set of triangles maybe, and then I drop my bouncy ball on that surface. I have no idea which direction it's going to bounce.
Okay.
And so a small change in my initial condition of where I drop the ball results in a massive change in the output. And so in this way, the fractal surface can induce chaotic dynamics in the motion of the ball. Does that help?
Yeah, it does. Actually, it does. Because now what is kind of forcing the system to be chaotic is the fractal nature of the surface.
Yeah.
Like, because there's like so many irregularities, actually infinite many of irregularities if we're talking about chaotic surfaces, is what is generating this unpredictable behavior of the ball, of the bouncing ball.
Precisely.
All right, so now you're a researcher in the Max Planck here in Dresden, in the Max Planck for Complex Systems. And so you work in chaos.
Yep.
And so you see chaos in your, life.
In my everyday life. Yeah, it's everywhere.
So my question is that, like, where do you see chaos? What kind of system do you work on?
Actually, in the last few years, I've worked on a whole bunch of different systems because chaos really is everywhere. And as soon as you have these complex interactions, you get chaos there. Right now, what I'm working on is active turbulence, where we have some sort of fluid flow. But instead of just a simple fluid, fluid's never simple, but instead of just a fluid, you have things inside like bacteria, which are consuming fuel to provide energy into the system, and so you have this like internal injection, and so this is a super cool sort of physical substance, which lots of people have done great research on, and what I'm super interested in is how do we understand this chaos, because in this you get a whole bunch of turbulent patterns, and so then the question is why, how, and because this can arise in in biology, right? You take a bunch of bacteria and you put them on a plate and they swarm around in these chaotic patterns, and this is fascinating to me that in biology we see this, we see evidence of this kind of chaotic behavior, and then trying to quantify it and understand what's really going on here.
Okay. Why is this chaotic?
Yeah.
That's a really big question you're trying to answer in these systems.
Yeah.
Okay. And how do you approach this analysis? You do like theory, experiments, simulations? What do you do?
So personally, I don't do experiments. My PhD is in applied maths, so I stay out of the lab for the good of all involved.
Are you good at the lab, or you just don't want to try?
It's been a while, let's say. And never in biology yet. So having never studied biology, I think I'm probably best behind the computer doing theory and simulations.
Okay.
But there are plenty of other people who do experiments, and so I'm lucky to work with them. And they produce these beautiful data, which I can then just go and analyze and get results from. But then, also theory, and so then you try and model the system, and so you say, okay, what are the physics that describe these this motion, and then you try and make a model of it, and then you can do some theory from that, and then I do a lot of simulations, and that's something else I really enjoy, is this scientific computing side, and then you can do a bunch of simulations, and and explore what happens. And obviously in simulation, it's much easier than an experiment to tweak some parameter and say, okay, so let's say the energy is barely being injected, or we have a lot of energy, and in my simulations, that's just tap in a number and go. Whereas in experiments, they have to go do another experiment and try and get everything perfect. And so, that's what I do.
Yeah, it's tough. Doing experiments is always tough.
Yeah.
Now I only want you to give me wrong answers.
Okay.
Okay, only wrong answers. What does chaos mean?
It means we're all going to die.
How to embrace chaos?
Personally, I start with the left arm and then the right arm. I've seen people suggest the right arm first, but I think left arm first is more consistent.
Okay, that's a koala strategy, maybe?
Yeah.
How to code chaos?
Personally, I would strongly suggest you put on dark glasses first so that you can't see what you're doing, because it makes it more chaotic, right? And then you take out your Morse code machine and you close your eyes just for extra layer protection.
Okay, so you have
code some things.
Glasses, but you also close your eyes.
Yeah, sometimes you can see through your eyelids because of chaos.
Just make sure.
Yeah, I think that's the best way to code chaos.
Okay, this is how you do it in your research?
Yeah, of course. Ask my office mates. Yeah.
Okay. Where does chaos... I think this is a movie title. Where does chaos reigns?
Where does chaos reign?
Yeah. Governs.
In my heart. Chaos reigns in the rainforest.
In the forest? Really? Everything seems more chaotic in the forest.
Have you ever seen a squirrel eating another squirrel?
We're all gonna die. Yeah, where is Chaos Lab?
The government doesn't want you to know this, but Chaos Lab is about 100 kilometers below us right here in Dresden.
Here in Dresden? Like in this Bonum?
Yeah, this Bonum, you know.
Chaos is a ladder. This is not a question, but chaos is a ladder. What do you think about that?
A ladder.
A ladder, yeah.
It's either deep or really stupid. I'm not
It's
sure.
It's a very deep. So so I think this is a Game of Thrones line. Some guy in the Game of Thrones just thrives on the messiness of the politics of all all these families fighting together for the throne, and he thrives on this mess. And one of the lines, the most famous lines, is chaos is a ladder.
Okay, makes sense. Yeah. Well, I suppose I would say the same thing because I've got a job now as a person studying chaos. So for me, chaos has been a ladder from PhD to postdoc.
Makes total sense.
Yeah.
You need to finish the sentence, okay? That's the last part of the interview.
Is it a jail sentence?
Huh?
Is it a jail sentence that I have to finish?
No. Por favor. Okay, what I love about my job is
being able to explore interesting questions and being able to take a day and just read about something which is absolutely fascinating because I want to understand why is this the way it is, and that's my job, is to do that.
Find out stuff.
Yeah, find out.
So what I hate about my job is...
Oof. Hate is too strong a word. There's nothing I hate about my job.
Okay. What do you dislike about your job?
The times when I get stuck and I don't make progress for a week, and I feel like an absolute idiot. And you look back at the week and think, at the beginning of the week, my aim was to do this. I have done not this. And you get stuck and banging your head against the problem.
Yeah.
And then 2 weeks later, you discover a bug in your code. But
I feel like if you're a scientist, you need to deal a lot with frustration like that, right? How do you do that? How do you deal with this frustration?
It really varies. Sometimes I'll just go and complain with a friend until the frustration is worked out. But also, it's sort of the rough and the smooth, because I think also in life, but that there's a frustrating period now, but then there will come a breakthrough, and that's really exciting, and it makes it sort of worthwhile. And then when you have the breakthrough, this kind of makes up for all that.
If I didn't get into science, I would have.
Actually, I was this close to studying accounting at university.
Really?
I can't tell you how glad I am I didn't. But,
you're a musician.
I am. I try to be.
How many instruments do you play?
This depends. On
Right answers, please.
Right answers. Okay, how do you define play?
Okay. Playing an instrument is, you play and nobody's ears hurt. That's how I define playing an instrument.
Then I could probably push it to around 10.
Oh my gosh. 10 instruments. Okay. You're a genius, man. If I were a superhero, my name would be...
Ooh.
I have one name for you.
I mean, it has to have chaos in it, right?
Yeah.
Chaos worm.
Worm? Why worm?
So that's
Like bookworm? Like this kind of nerdy thing?
Yeah. And then I don't know what my superpower would be. Just being completely unpredictable.
Oh wow, that's an incredible superpower because, when you fight someone, you need to anticipate what the other person would do to be able to block him or whatever. And if you're completely unpredictable, you'll be invincible.
And even I can't predict myself, so exactly. I don't know what I'm going to do. You don't know what I'm going to do.
Wow, that's an incredible superpower, actually.
Yeah.
Well, thank you, Malcolm. That was super fun and super interesting as well. So thank you for coming to my channel.
No, thank you for inviting me. It was super great to be here. I
said chaos too many times.
Chaos!